In this episode, we will talk about systematic meta-abilities alignment in large reasoning models. You've likely noticed the really remarkable progress in large reasoning models recently. I mean, models like OpenAI o1, o3, DeepSeek R1, Grok 3.5, Gemini 2.5 Pro, they're showing some incredibly sophisticated long chain of thought reasoning, and even behaviors that look a lot like reflection.
That's right. And, a particularly interesting aspect is how these advanced capabilities seem to pop up. Sometimes people call it the aha moment, that sudden insight which seems to emerge through reinforcement learning. We've seen this in models like DeepSeek R1, and has been replicated in open source projects too, like SimpleRL Zoo and TinyZero. It's almost like the models stumble upon better ways to think.
Yeah, like they
Yeah.
suddenly just get something they didn't before. But,
Mhm.
well, these emergent aha moments are fascinating, but trying to build reliable reasoning systems by just hoping for them, that feels inherently risky, wouldn't you say? It adds this unpredictability that could really hold things back.
Absolutely. That unpredictability is a major hurdle for reliability and, ultimately for scaling up these reasoning capabilities.
Right.
If you can't reliably get these aha moments to happen, it's tough to engineer systems you can depend on for important stuff. Plus, it makes it harder to figure out why a model actually worked or didn't work on a specific problem.
And that's exactly where this research comes in, right? Instead of just waiting for these spontaneous moments, the researchers are trying something more direct, explicitly teaching the model's fundamental reasoning abilities. It feels much more like an engineering approach, more controlled.
Precisely. The core idea is to systematically build in what they call three-domain general reasoning meta abilities. These aren't specific skills for one task, but more like fundamental ways of thinking that apply broadly. They're drawing on the classic trio of inference: deduction, induction, and abduction.
Okay, let's break those down. Deduction. That's inferring specific things from general rules, right? Like if A implies B and A is true, then B must be true. So hypothesis plus rule gets you to an observation.
Exactly. Deduction is all about logical certainty. Given a rule and a hypothesis, you can figure out what must follow. Think of it like solving a geometry proof step by step from the axioms.
Right. Then there's induction. That feels like the opposite direction. You see lots of specific examples happening together, and you try to figure out the general rule. So hypothesis plus observation leads you to the rule. It's about spotting patterns and generalizing.
Exactly right. Induction is fundamental to how we learn from experience. You notice things tend to happen together, so you infer an underlying rule. It's how we generalize from seeing a few examples to understanding a broader concept.
Okay, and the third one, abduction. This sounds more like making an educated guess, finding the best explanation. When you see something surprising, abduction is figuring out the most likely cause or hypothesis, given what you already know. So, observation plus a rule helps you infer the hypothesis.
That's a great way to put it. Abduction is often described as inference to the best explanation. You're working backward from an effect, and the rules, you're trying to pinpoint the most plausible cause. It's common in, say, medical diagnosis or figuring out why some system failed unexpectedly.
So, these three, deduction, induction, abduction, they don't just work in isolation, do they? The paper suggests they kind of form a loop, almost like the scientific method itself. You observe something, use abduction to form a hypothesis, use deduction to predict consequences, test them, and maybe use induction to refine your rules based on the results.
Exactly, it's a cycle. You might start with something puzzling. Observation. Guess why? Abduction. Figure out what else should be true if your guess is right. Deduction. Check that out. Observation. And maybe update your understanding of the rules. Induction. That whole loop is what supports really robust thinking.
That framework makes a lot of sense conceptually. But how do you actually teach these abstract skills to a huge language model? It's not like just feeding it labeled images.
Right, and that's the clever part of their methodology. They created a whole suite of tasks, specifically designed to push the model to use each of these reasoning modes. And crucially, these tasks can be generated automatically and checked automatically, which means they could create tons of training data without needing humans to label everything.
Ah, automatic generation and verification, that's key for scale. Okay, so for deduction, what kind of task force is that logical step-by-step reasoning?
They use propositional satisfiability tasks. Basically, you give the model a set of logical statements like if P, then Q, and P is true,
Yeah.
and ask if a conclusion like Q is true logically follows without any contradictions. The model has to check if all the Boolean formulas can be true at the same time.
So it's like giving it little logic puzzles. Here are the rules, here are some facts, is this conclusion valid?
Exactly. And they can make these puzzles quite complex with lots of interconnected statement, so the model really has to follow the logical chain, not just guess.
Okay, that covers deduction. How did they target induction? Getting it to generalize from examples.
For induction, they used masked sequence completion. Imagine a sequence like numbers or symbols that follows some hidden rule. They'd hide some elements in the sequence, and the model's job is to figure out the underlying pattern from the parts it can see and then predict the missing pieces correctly.
Ah, like those what comes next in the sequence
Yeah.
problems. The model has to induce the rule generating the sequence. Were the rules complicated?
They could be, ranging from simple arithmetic stuff to more complex patterns. The point was to make it really abstract the rule, not just match surface patterns it might have seen before.
Makes sense. And finally, abduction, inferring the best explanation. How do you make a task for that?
They came up with something called inverse rule graph search. Think of a network where nodes are facts and the connections are rules, like fact A implies fact B. The model sees some resulting facts, nodes, and the map of the rules. Its task is to work backward and figure out the minimal set of starting facts, premises, that would logically lead to the observed results following the rules.
So it's like seeing the final scene of a play and having to figure out the most likely starting conditions and sequence of events that led there, given the known rules of how characters behave.
That's a really good analogy, yes.
Yeah.
It has to find the simplest, most consistent causal path backward through the rule network to explain what it's seeing.
And it was important that these tasks were really different from the usual text data these models are trained on, right? To make sure they're actually learning the reasoning skill itself.
Absolutely critical. They specifically designed this synthetic data to be statistically distinct from typical web text or books. The goal was to ensure any improvement came from genuinely learning deduction, induction, or abduction, not just from recognizing patterns similar to things in the pre-training data.
Okay, so they have this suite of tasks. How did they actually train the models? The outline mentioned a three-stage pipeline. Can you walk us through those stages?
Sure, it was a three-step process. First, they focused on aligning individual models to each meta ability separately. Second, they merged the parameters of these specialized models together. And third, they did further refinement using domain-specific reinforcement learning.
Let's dig into Stage A meta-abilities alignment. They had these three synthetic data sets. How did the training actually work for each specialist model? The deduction one, the induction one, and the abduction one.
Okay, so in this first stage, they took 3 separate copies of their base model and trained each one to specialize. One for deduction, one for induction, one for abduction. For the training itself, they used a specific reinforcement learning technique called critic-free reinforce plus Wessels. They also incorporated some improvements from another framework known as Logic RL. Basically, reinforce plus plus is a way to directly tweak the model's behavior based on rewards without needing a separate critic model to judge things along the way.
Right. And the reward system, how did they signal to the model whether it was doing good deduction or good induction or good abduction?
It had 2 parts, a format reward and an answer reward. The format reward was pretty simple. It just encouraged the model to structure its output properly, using specific tags like think for its reasoning steps and answer for the final result. Using the right format got a positive reward, messing it up got a negative one. So it learns to show its work, essentially.
That encourages interpretability too, which is nice. And the answer reward, that's about getting it right.
Exactly. The answer reward judged if the content of the answer tag was actually correct for the specific task. For deduction, that meant satisfying all the logic formulas. For induction, it meant predicting the missing sequence element correctly based on the pattern. And for abduction, it meant finding the minimal set of premises that consistently explain the observations via the rule graph. Correct answer gets a positive reward, wrong answer gets a negative one. And importantly, these rewards were normalized across a batch of responses to help keep the training stable.
Okay, so after Stage A, they have 3 expert models, each good at one meta ability. Stage B is parameter space merging. This sounds efficient, combining them without more training. How does that work?
Yeah, it's a pretty neat and cost-effective trick. Parameter space merging lets you blend the knowledge learned by different models directly at the parameter level, the weights and biases inside the neural network. You take the parameters from the deduction model, let's call them eta, the induction parameters eta I, and the abduction parameters, and you compute a new set of parameters for a single merged model, merge, basically by averaging them together but using weights.
Like creating a blended whiskey, maybe. You combine the characteristics of different single malts, but not necessarily in equal proportions.
That's a decent analogy. The formula is straightforward. Merge equals some weight, lambda times D plus lambda I times A plus lambda times A. These lambdas are just numbers that control how much influence each specialist model has on the final mix.
And how did they figure out the best weights, the best lambdas? Did they just guess or?
No, they found the best values empirically. They tried different combinations of weights and saw which resulting merged model performed best on some validation tasks. Interestingly, they found unequal weights worked best. The optimal mix they reported was lambda equal 1.0, lambda equals 0.2, and lambda equals 0.1. So the deduction model's parameters got the biggest weight in the final merged model, at least initially.
Huh, interesting. So deduction was weighted most heavily. Okay, so this merging gives them a single model with hopefully blended capabilities, and that model becomes the starting point for stage C, domain-specific reinforcement learning. What's the idea here?
The idea is to take this model that's already got a foundation in these general meta abilities and fine-tune it further on tasks from a specific area. In their study, they focused on math problems, using the same setup as the simple RL-Zoo project. The question they're asking is, does starting with this meta-ability foundation help the model learn domain-specific skills better or faster than starting from just a standard instruction-tuned model?
And what RL method did they use here? Was it reinforce plus plus again?
No. For this stage, they used a simpler reward. Just +1 for a correct final answer, 0 otherwise. And they use a different RL objective called Group Relative Policy Optimization, or GRPO. These choices were specifically made to match the simpler RL-Zoo setup so they could directly compare their approach against models trained the standard way instruction tuning, followed by the same GRPO procedure, but without the meta-ability pre-training. GRPO basically tries to make the model rank correct answers higher than incorrect ones within a batch of generated responses.
Okay, that makes the comparison fair. So after all this, the alignment, the merging, the domain-specific RL, how did the models actually perform? They tested them on a bunch of benchmarks, right? Math, coding, science.
Yes, they used a pretty broad set of 7 benchmarks. For math, they had Math 500, the historical AIM problems, American Invitational Mathematics Examination from 1983 to 2024, recent AMC 2023 problems, A&E 2024, and a tough Olympiad set called OmniMath. For coding, they use Live Code Bench, and for science questions, they use GPQA, which has graduate-level questions.
Quite a range. And how did they measure success?
Mostly using pass at one, basically. Does the model get the right answer on its first try with deterministic settings, temperature 0.0? But for AIM 2024 and AMC 2023, which have fewer problems, they used average accuracy over 32 tries, allowing for more randomness in generation. Temperature 1.0, top end 0.95.
And the big question, did the metability alignment actually help? How did they stack up against regular instruction-tuned models?
The results were pretty positive, yeah. Even the models only trained on the synthetic metability tasks before the domain-specific RL showed performance gains over the instruction-tuned baselines on these real-world benchmarks. That's pretty significant, suggesting these abstract reasoning skills actually transfer. The paper has tables showing the specific numbers for the 7B and 32B models, comparing them to the baselines across all benchmarks.
Wow, so just learning deduction, induction, and abduction on fake data made them better at real math and coding. That is remarkable. Did the individual specialist models show different strengths? Like, was the deduction model better at math logic?
There were some differences, yes. For the smaller 7 billion parameter models, the induction-aligned model actually had the best average improvement across all benchmarks. But interestingly, the deduction-aligned model did show the biggest jump, specifically on Math 500, which often needs that kind of rigorous, proof-like reasoning. It hints that different abilities might be more crucial for different kinds of problems. Again, Table 1 in the paper breaks this down model by model, benchmark by benchmark.
And the merged models, did combining the specialists pay off?
It definitely did. The merged models, both 7B and 32B, consistently did better than the standard instruction-tuned baselines across pretty much everything. It shows that the parameter merging wasn't just averaging things out, it was constructively combining the different learned skills. Table 1 shows those gains clearly.
They also mentioned an oracle ensemble. What was that about?
Yeah. The oracle ensemble was more of a theoretical test. They looked at the answers from the 3 specialist models, deduction, induction, and abduction, for each problem. If any one of them got the right answer, the oracle ensemble was considered correct. It consistently scored even higher, especially on math. This suggests that the different models were often making different mistakes. They were complementary. It points towards potential for even bigger gains if we could find smarter ways to combine their outputs beyond just parameter merging.
That complementarity is really interesting. Okay, now stage C results the domain-specific RL on math. Did starting from the meta-ability merged model give them a head start?
Yes, and this was a really key result. When they fine-tuned on math problems using GRPO, starting from their meta-ability merged model, which they call domain ARL meta, consistently led to better final performance than starting the same GRPO process from a standard instruction tune model, domain RL ins. It suggests that having that foundational grounding in deduction, induction, and abduction actually raises the ceiling of what can be achieved with further domain-specific training.
And were the improvements significant? Did it scale with model size?
They were definitely significant, especially on the harder math sets like AMA and the Olympiad problems. And yes, the effect was even more pronounced with the larger 32 billion parameter model. The performance gap between starting with meta abilities versus just instruction tuning widened with the bigger model. This suggests the whole approach scales well. Table 2 in the paper has all the detailed comparisons for domain RLNs versus domain RL meta on the math subsets for both 7B and 32B models.
So wrapping it up, it sounds like this approach of explicitly teaching deduction, induction, and abduction offers a more systematic, controllable way to boost reasoning in these large models. It moves beyond just hoping for aha moments.
That's a great summary. It provides a strong argument for this kind of structured alignment. It seems to lead to more capable models, better generalization, and even improves how much they benefit from later, more specialized training. It's a pathway towards more robust AI reasoning.
And it opens up interesting future work too, right? Better ways to merge the skills, maybe applying it to images or sound, and potentially improving safety and interpretability because you have a better handle on how the model is reasoning.
Exactly. That oracle result showing complementarity is a big hint that better fusion techniques could yield more gains. And extending this to multimodal data is a natural next step. Plus, if you can encourage or track the use of specific reasoning modes, deduction versus abduction, say it might give us more insight into the model's process, which is crucial for trust.
It really makes you think differently about teaching AI, moving towards instilling these fundamental cognitive building blocks.
It does. It's less about just pattern matching on vast data
Yeah.
and more about equipping the AI with the core tools of thought. It feels like a step towards systems that don't just mimic understanding, but might actually reason more robustly and solve problems more effectively.
A really fascinating direction for AI development. Thanks for walking us through this research.
My pleasure. It's definitely thought-provoking work with potentially big implications.